All right, welcome to video lecture number 7. We are almost there, just this one and the next one. In video lecture 7, we are going to be talking about correlation and simple linear regression. In both of these cases, we're going to be examining relationships between two quantitative variables. So in the last lecture, we talked about chi-square tests, where we're looking at relationships between two categorical variables. So in this one, we're going to talk about the same type, but what do you do if those variables are quantitative? All right, this is just a slide that brings us up to speed in talking about correlation. So far we've examined descriptive statistics for a single variable. And if you remember, those were our measures of central tendency and our measures of spread or variation. And then we did some graphical representations around that. We then decided to examine differences between groups. And so we had different tests that we looked at. We had the one sample Z test, we had the T tests, and there were 4 of them. The one sample t-test, the dependent samples t-test, the independent samples t-test, there were 3 there, and then ANOVA was the 4th test. We looked at that lecture, so that was difference between more than 2 groups. And we've also just, as I just said, looked at relationships between 2 categorical variables. So today we want to look about examining relationships with 2 quantitative variables. And to do that, we can use a correlation. If you remember back to our first lecture when we talked about visualizing information and visualizing data, one of the plots we looked at was scatter plots, which we said were the best when we're examining 2 relationships between quantitative variables. And I think the example I kept using was height and weight. So here we have an example of that. We've got a table that shows you each case number. So this is an individual. Their height is 59 inches and their weight is 92 pounds, okay? So we can create a plot where on the y-axis I have weight, which is in pounds, and on the x-axis I have height, which is in inches. And then I can go in here and say, okay, well, this is 59 and this is 92. And so I can make a little dot for case number 1. And I can do that for all 20 cases here in the scatter plot. So there are 20. Okay? And that gives us a visual representation of the relationship between height and weight for these 20 cases, or for this sample. Okay, when we think about correlation, you want to think about 2 things. The first one is the direction of the relationship, and the second one is the strength. So the direction is what happens when one of the variables increases. Does the other increase as well? Then we'd say that direction is positive. Well, what happens if one increases and the other decreases? Then that would be a negative direction, okay? And then strength is, well, how strong is that? Is it true for every single individual or case? Or are there some where it's a little, not perfect? So if we go back to the height and weight example, there are, of course, tall people who don't weigh a lot. They're very skinny, right? And so that's an example where it's not a perfect relationship, but in general, taller people are heavier, right? And so that would be a strong positive correlation between those 2. So pause the video and go ahead and try to label each one of these 8 scatter plots with the identifiers that I have. And you're back, okay? So you should have labeled each one of these. I'm going to go through now and talk through the ones that I have. So in this first one, notice that as y is high, x is low. So as one is high, the other is low. So that would be a negative relationship. And now I need to think about the strength. Well, it's not right on the line, right? And it's not as tight as it could be. So I would think that this is a moderate and negative relationship, or D. So I'm going to cross that one off. Okay, for this next one, as x is low, y is low, and as x is high, y is high, and these all fit on a line, so that's going to be a perfect relationship, and it will be positive, E. So I'll cross that off and label E there. Sorry, that doesn't look like an E. Okay. For this next one, it just sort of looks like a cloud, right? If I were to draw a cloud around this, the cloud doesn't seem to have much of a relationship. So I would say that that is G, non-existent. For this one, is X is low, Y is low, and is X is high, Y is high, but there's a little bit of noise around that, right? They don't all fit on a perfect line, but that's pretty close. So I would say that this is strong and positive, A. Cross that one off. Okay, this one, they all fit on a line, and as Y is high, X is low, and when X is high, Y is low. So we know that this is a perfect and negative relationship. All right, and this one we have one being low and the other one's low. When one's high, the other seems to be high, but there's quite a bit of distance between some of these. So I would say that's moderate and positive, C. On this one, if you were to kind of fit a line to this, you'd see that it would be a curve, right? So one of our options here is curvilinear. That would be H. And then finally, as Y is high, X is low, they're pretty tightly scattered around a line, so that is going to be strong and negative with B. So hopefully you were able to identify each one of those. Okay, so now we get to correlation. Before we just looked at some scatter plots, but correlation is kind of a quantitative and precise measure of how each of these variables is related to the other. It's a way to quantify this relationship. So if variable X increases, what happens to variable Y? Does it increase or decrease, or is it unaffected? If it increases, then it's a positive correlation. If it decreases, then it's a negative correlation. And if it's unaffected, we'd say there's really no correlation here, right? Correlation, as we saw in the scatter plots, it also measures how tight the relationship is. That is the strength of the relationship. So as we get closer to 1, that's a strong positive correlation. And as we get closer to -1, that's a strong negative correlation. Correlation also describes the amount of variability that's shared by these two variables. So we'll talk about this a little bit more later, but you can think about the height and weight example and how there are common factors affecting how tall you are and how much you weigh. And that could be nutrition, age, medical history, health, genetics, etc., right? So there's going to be some shared variability between both height and weight that correlation will help us explain. And finally, as I sort of talked about, correlation is bounded by -1 and 1. Okay, so I didn't have the process slide. I know you all have it memorized at this point, but we are still going to do a hypothesis testing procedure with correlation. So remember, the first step is to establish our null hypothesis, which we'll test against, and then, of course, our alternative as well. So take a moment and think about, what do you think the null hypothesis would be with respect to the correlation statistic? All right, so you should have gotten that the null hypothesis would be that there is no correlation, or that the correlation is 0. So the Greek letter that we use here for correlation, remember we're always using these Greek letters to signal what's the correlation in the population that I'm testing about, right? Because we're making inferences from our sample to the population. We use the Greek letter rho. Okay, so rho is equal to 0 would be our null hypothesis. All right, a statistician that discovered this test, it's called the Pearson's correlation test statistic. What he discovered was that if he standardized 2 quantitative variables, and remember what that is, you go ahead and standardize it by making the mean of 0 and the standard deviation of 1. If he standardized 2 quantitative variables and tracked the relationship between those z values for each individual case, then he found that if the 2 distributions tracked each other closely, then his calculation approached +1. And if they if they tracked each other in an inverse direction, the two distributions tracked each other in an inverse direction, then his calculation approached -1. So on the next slide, I'll show you the Pearson's R correlation test statistic formula. Okay, so here's the Pearson's correlation test statistic. It is the sum of the cross product of the z-scores divided by 1 minus the sample size. So look through this table for just a minute. We have 10 cases, 10 individuals. For each one of them, I gathered information about some quantitative variable, let's call it x, and then I standardized that. And so you can see it's standardized from -1.49 to 1.49. And then I get information from a different variable, this is y, and that's also ordered from 105 to 190, but I take the z-score of that to standardize it, so now they're on the same distributional scale. And I multiply both of those z-scores, and I add them up. And so if you do all that, you get the sum of the cross product of 8.68. Well, that's the numerator in this example, so 8.68. And I know my n is going to be 10 down here. So 10 minus 1 is 9. And if I do that calculation, I get a correlation coefficient of 0.96. So what does that tell us? Well, it tells us strength and direction. First, the direction is positive. That means as x goes up, y should go up. And if you look at our data, you notice that. It's ordered from 20 to 65 and from 105 to 190, and they pretty much fall in line there, 10 cases. But it also tells me the strength of this relationship. And so you can see that the degree to which these two variables are associated is quite strong at 0.96. A perfect relationship would be 1, so it's a very strong relationship and it's positive. Okay, well here is the computational formula. In the previous page it was a little easier because we had the z-score sort of standardizing things for us. This brings it all together, so it's a little messier, but I think the simpler version is to think about it. What's happening is we're looking at how do x and y co-vary, that is, how do they vary together? And then we're taking that covariance and we're standardizing it by using the standard deviation of x and the standard deviation of y. So down here, notice this formula is what I just described. What's the covariance, or how do x and y covary? And then how do we use both of their standard deviations to standardize that covariance? Now the messy formula is you take the sum of the cross product of x and y times the sample size and subtract off the sum of x times the sum of y. And all of that's divided by, and you can read this formula, but you basically have the standard deviation of x, which is that n, the sum of x squared minus sum of x squared, times n sum of y squared minus sum of y squared. All right, so that formula, we could do in Excel. We can move through each one of these columns and figure it out. Of course, Stata can do this calculation for us, but I want you to, theoretically, if we're thinking about it, we're just thinking about how do these two variables move together, and let's standardize them. Let's see how they covary, and then we're going to standardize that so that they're on the same distributional scale. So if one's weight and one's height, or one's a math score, one's a reading score, I can still use them together to find out my correlation. So this value of R is referred to as the correlation coefficient. And the absolute value of R represents the strength of this relationship. So the closer we get to 1, and that could be -1 or +1, the stronger the correlation. And in general, this is a little scale that people think about. If the correlation is between 0 and 0.2, that's no relationship to a very weak one. Weak's 0.2 to 0.4. Moderate's 0.4 to 0.6, strong is 0.6 to 0.8, and then above 0.8 is a very strong, all the way up to 1 or -1, which would be a perfect association. Okay, now we come to what we call the R-square, or the coefficient of determination. When we square R, it becomes the coefficient of determination. Basically, it says the percent of the variance or the variability in one variable that can be accounted for by the variance in another variable. So what's what are the two things that are co-varying together? Okay, some common factor or set of factors that do that. So the stronger the correlation, the more variance can be explained, or the greater the R squared. So if we determine that our correlation is 0.6, so that's a moderate correlation. If we square R6, we get R squared of 0.36. And what that says is that 36% of the variance in one variable is attributed to variance in another variable, okay? And it doesn't posit a direction. It's just they're both doing it for each other. But 36% of the variance in one variable is attributable to variance in another. Okay, I'm visual. I like to say these things visually. So go ahead and when you get a chance, click on this link, and you may need to be in the slides that you get that you download. But if you click on this link, it'll allow you to visualize correlation. You can change the sample size, and you can drag that slide me bar to the left and right. And what it's going to show you is the shared variance, or that R squared. And you're going to see these two circles, the two variables, coming together. And that's kind of a way to visually represent how these two things share variance. So it creates a bit of a Venn diagram. And you'll notice as the correlation goes up in either direction, that shared variance increases, or more of these circles overlap. All right, now in the social sciences, we're not often just interested in relationships between two variables, but we want to explain one of the variables by variation in the other variable. So how is changes in y explained by changes in x? So some examples might include, how does a change in state per pupil expenditure affect SAT scores, for example? Or how does hourly wage vary with levels of education? So in that case, levels of education might predict hourly wage. Or how does student attendance vary with parental involvement? So is parental involvement influencing how often a student comes to school? Or how does gender influence math test scores? Often we thought about the gender gaps, particularly 70s and 80s, 90s. We had a big thing about, women were performing substantially lower on math scores than men. And the question was, is this genetic? What are the reasons for this? And there's a great book, Whistling Vivaldi, that you should all read, that talks about how it's even just the stereotype throughout. It's the perception that you may do worse can often affect how you perform on it. But that might be something you're interested in looking at, right? How does gender influence math test scores? All right, so the simple regression model examines the relationship between two variables. In this sense, I want us to think about them as quantitative variables. The x variable is the independent variable, or as we learned with the chi-square test, we can call this the explanatory variable, the control variable, the predictor variable, the regressor, or the right-hand side variable. And you'll see why we call it that. The y variable is the dependent variable, and that's the explained one, the response variable, the predicted variable, the regressant, or the left-hand side variable. So an example might be that if I were given I could create a regression equation that defines a relationship between students' socioeconomic status, that would be the independent variable, and students' math test score, that would be the dependent variable. And I could predict a student's math score if I know their SES level. So prediction becomes part of this. Once you fit the model, you now know something, you're stating something about the conditions in the world, and you could say, well, give me a student and tell me their SES, and with some degree of precision, I could tell you what I believe their math test score would be. So a linear regression allows us to make those predictions. Okay, so as I just introduced in the previous slide, prediction then becomes an activity that allows us to compute future outcomes from the present ones that we have. So we take observed data, observational data that we have and we've gathered, and it allows us to make predictions based on data that we don't have yet, conditions in the world. So what if we want to predict college GPA based on high school GPA? So take a moment and write down the dependent variable and independent variable in each one in this example. Okay, you should have written it down. I'm going to go ahead and do it here on the slide. So if you haven't, pause it and do it. But it looks like we're predicting college GPA. So that's going to be the downstream variable, right? So college GPA will be the dependent variable, and the independent variable will be high school GPA. Now I like this one because it gives us a temporal order. We know that we go to high school before we can go to college, so it helps us think about dependent and independent variables. So the upstream variable, or the one that comes first, is high school GPA, predicting the downstream variable, or the one that'll respond, which is college GPA. Okay, so just like we did at the beginning of this lecture, we can gather some data and create a scatter plot. So now I have students who have a first year's college GPA, and I know their high school GPA. And so I can make a table here of both of those. So I have student number 1 right here. They got a 3.5 in high school, and their first year they got a 3.3. And so then I could go in and I could plot that. Well, they got a 3.5 in high school. They got a 3.3, so it looks like they're right here. Somewhere around there, right? And we can do that for each one. So this case here, looks like this person got 1.9 in high school and a 2.0 in college. So that looks like that case is right there. So we went ahead and plotted each one of these to creating the scatter plot. Okay, now onto our scatter plot, we can put a fitted line, or a line of best fit, or a regression line. It's going to be defined by an equation, a linear equation that we'll go through in a few slides. But right now, for this slide, the idea is that I can fit a line that's going to define this relationship. It's the regression line, and we say of y, the dependent variable, on x. So college GPA on high school GPA, y on x. So now this line, practically speaking, becomes something pretty powerful for us if we, from our sample, want to generalize now to a broader population. We can use this line to determine future outcomes. So we might say, well, if you have a high school GPA of 3.0, based on the sample that I have, you are predicted to have a college GPA of about, what is that, 2.85, something close to that. So the idea is that I can draw and figure out what, to use this regression line to predict for outcomes that I don't have, that aren't included in the sample, using that line of best fit. Okay, so here is the simple regression model, okay? So y, which is the dependent variable, is defined by an intercept. It's defined by the x variable, the independent variable x, the slope of the line, which we define by beta 1, and all the other unobserved factors that affect the variation of y not captured by x. So it's just kind of like everything else I didn't include in the model. So if we were to think about the example we just have, it would be that college GPA is predicted by an intercept plus high school GPA and a line that defines that relationship plus everything else that affects how you do in college, right? All the other things that affect your college GPA, and that's represented by U, or sort of the error term. Now with this model, we make one very important assumption, okay? If we're going to use it to predict outcomes. That assumption is that the independent variable x is unrelated or uncorrelated with the error term U, okay? That is, knowing something about x does not provide me with any information about U. So mathematically, that's rho of xu equals 0. Okay, there's no correlation between those two. Now, you might think to yourself, that's a pretty strong assumption, right? Is there something that about me that influences my high school GPA that might also influence my college GPA that may not be captured, right, in this model? And that would be contained in that U. So if those two things are correlated, then we would violate this assumption. But for now, the simple regression model, for it to work, it makes this important assumption that knowing something about my independent variable x doesn't tell me anything about all the other things that relate to y. Okay, so take a moment and just think about it. What other variables might be contained here in the error term, or U? That is, what other factors influence your college GPA? And so take a moment. I think it's nice to do a step-by-step process. So take a moment and think about what are some factors that influence my college GPA? Write those down. And then the question is, did anything that you listed in that list, does it also influence your high school GPA? Is there common factors? And if so, then that means that that X and that U will be correlated and that you'll violate that assumption. And your prediction, your beta 1, right, your linear fit that you create, that's going to be biased by those variables because it's going to capture not just the relationship between high school GPA and college, but all those other things that are correlated with both high school GPA and college GPA. So it's going to be maybe a biased upwards. It's going to be too large of an effect because you haven't accounted for those things. So pause the video, go through that exercise, and then unpause it, and I'll just talk through a few ideas. Okay, so coming back, now I love doing that. I'm waiting a second and then coming back. So coming back now, think about all the things that we don't capture in this model. So what influences our college GPA? Well, are we working, right? Well, why might you need to work? Financial situation. What about my health status? What about my race, ethnicity? What about, the type of environment I grew up in? What about my mental health? There's a host of things, right, that you could say, well, that's going to influence my high school GPA as well as my college GPA. They may be common factors. So if we're in the simple regression model, we only include one variable, right? But in this case, we need to be careful positing a causal relationship because we know that the estimate that I create, that beta 1, that relationship, is going to be biased because it's not capturing these other things that are correlated with both high school GPA and college GPA. That is, that error term and X aren't uncorrelated. There is a correlation there. And so we're violating that assumption. Okay, so let's make that assumption though. Let's make this assumption that X and U are uncorrelated. Then the regression equation becomes Y equals beta naught plus beta 1X, okay? Or the intercept term plus the slope term defined by the independent variable X. Or in a form you may be comfortable with or more familiar with when you think back to algebra class is Y equals MX plus B. And that is the formula for a line, right? So this implies that for every unit increase in X, there will be a constant change in Y defined by the slope term beta 1. So for a unit increase in X, I get a beta 1 change in Y. All right, so now we have a regression equation. Sorry that overlapped. I thought I fixed that. That really bugs me. All right, so given the following equation, Y equals the intercept term, so it's anchored at 45.2, that's where it crosses that Y-intercept, plus 3.5x, okay? Where X is a student's socioeconomic status and Y is their reading score. My first question, go ahead and work out this slide, pause it, and then I'm gonna go ahead and work through it as well. So pause it now. And we're back, all right? I'm gonna go ahead and work through each one of these. Okay, so what is my independent variable? Well, my independent variable X is defined by, remember that's going to be, we called it our right-hand side variable. Now you see why it's on the right-hand side of that equation, that equal sign. So the right-hand side variable X is SES And my dependent variable y is EOG reading score, which my daughter just took 2 days ago. All right, so the question now is, well, I have a formula. Can I predict a score, a reading score for a student with an SES level? So now I'm giving you the X value, and we go ahead and just plug it into the equation. So y equals 45.2 plus 3.5, and now I know their SES level is negative 2.5, okay? And if I run that, their predicted EOG reading score I get is 36.45, okay? Now I get to do it number 2 for 3.2. Y equals 45.2, that intercept term, plus 3.5, that relationship, that line's constant. But what can change is the X value. And in this case, I want 3.2. That's this person's SES. So they're predicted to score 56.4. Okay. Now this last one's a little different. It's saying, well, what's the predicted EOG difference between a student with an SES level that's negative 1.5 and an SES level that's 2.4? All right. So I need to do 2 equations. The first one, I'll do 45.2 plus 3.5 times negative 1.5, and I get 39.95. My other y would be the same equation, but now I'm going to plug in 2.4, and I get 53.6. And if I take the difference of these two, I get 13.65 points. So if you give me a student that has an SES level of negative 1.5, and then their student sitting next to them has an SES level of 2.4, I can give you some prediction of their difference, and that's over 13 points. It's pretty stark. It's pretty dramatic here, okay? And then the question is, it seems like this SES is centered around 0. So if I have a student who's just right in the middle income in the sense of on this SES scale, notice that their predicted score, if I were to plug in a 0 here, would just be 45.2, where that intercept is. That's where X equals 0. And I have a slide on that, which I didn't realize I had. But now it's cleaner, easier to follow. All right. Okay. So you'll notice here we have 2 unknowns we need to calculate. So I can, in my observable data, I have my dependent variable y, and I have information for my independent variable x, but I need to calculate a slope parameter and an intercept. So we actually start with the slope parameter, and here is the formula for it. And I know it looks a little scary. So start with the lower, another way to think about this, which is that beta 1 is the covariance right here. Beta 1's the covariance of x and y. So how do x and y move together? We talked about that with correlation. Divided by the variance of x, okay? And that's pretty much what we're doing here in this formula above. Beta 1's calculated by taking each individual x difference multiplied by each individual y difference, and then we're summing all of those through all of our observations, and we're dividing that by each of the deviations of the x from the x bar, or that variance. Remember, this should look pretty familiar to you in the sense that we have here these formula that are very similar to the standard deviation formula, but we don't have the square root sign. So it's more like that variance formula where we squared that. So what the implications for this are is that if x and y are positively correlated, then the slope will be positive. And that makes sense. If you think about that scatter plot, if the line of best fit is going up, if it's positive, if that cloud's looking positive, then it will be a positive slope. But if x and y are negatively correlated, then it will be a negative slope. Okay? And notice here, because we have x on the denominator, it cannot be 0. That means it has to have some variation. And this makes sense. If x doesn't vary at all, well, of course it can't predict any of y's variation because there's no variation in x. Okay? So it's just the intuitive sense is if my independent variable doesn't vary, then there's nothing really to predict with that variable, right? Because there's no variation there. All right, having calculated my slope parameter, beta 1, it's now easier for me to calculate, pretty straightforward for me to calculate the intercept. So how I do that is my beta 1 is equal to the mean, the sample mean of the dependent variable minus that beta 1 I just calculated times the sample mean of the x variable, okay? And that'll get you beta naught. So again, Stata is going to do these calculations for us. It's going to give us the intercept parameter. It's going to give us the slope parameter. But these are the conceptual understandings. We're thinking about, well, how do x and y covary, and standardizing that over x. And then we're thinking about, well, we need to anchor that line on some intercept. And so I do that by using the means of x and y and that beta 1 that I just calculated. Okay, so let's go ahead and figure out the big thing with simple linear regression and then multiple regression, which we'll talk about in the next lecture. For me, is I would love you to walk away knowing how to interpret these coefficients. Their interpretation is really important. So let's go ahead and do this together with an example. So we have wage, hourly wage in dollars. That's defined by this variable wage here. Excuse me, hourly wage in dollars. All right, and then we have our intercept, which is negative 0.9. And then we have this slope parameter, beta 1. So this is our beta 0. Beta 1, which is 0.54, times years of education. So this it seems a little nonsensical, right? And we're going to talk about it in the next slide when we actually go through this, but as we interpret it. But if the years of education are 0, then the hourly wage is negative 0.9, which doesn't make sense, right? You can't make a negative amount of money. But the idea is that's some of the weaknesses of simple linear regression in the sense that that line is going to go in a straight line and needs to anchor somewhere. And since our sample generally doesn't have people with 0 years of education, or if it does, it doesn't have great estimates on it, a lot of our data is going to lie up with people that have values. And so we can talk about this more in class, but the idea is that that straight line can predict for any value of level of education. And in some senses, you get a wage return that's a little bit nonsensical. Okay, so just to kind of put that in a bullet point, so you have it here. This equation is saying that for an individual with 0 years experience, their average hourly wage is negative $0.9. Okay, so it's about negative 90 cents. But what it's saying, though, is for each additional year of schooling that individual has, so 1 year, 2 years, 3 years, for each additional year of schooling, their hourly wage is predicted to increase by 54 cents. That's that 0.54. Okay, it's expressed in terms of dollars, the dependent variable wage. So go ahead and do the calculation. If I have 12 years of education, what would my hourly wage be? Well, here it's pretty straightforward, right? We take our formula and we plug in the years of education that we have for the educ variable. So here we get, if we run that equation out, you can see here we get an average hourly wage for an individual with 12 years of education, so a high school diploma, of $5.58. All right, so now let's practice interpreting regression coefficients. If you work with a partner, that would be great. If you have someone in your house who say, hey, I just learned this really cool thing about regression, we're going to do it together. But if not, I'm your partner. So let's work together to interpret these. If you want to pause it and do it alone and then come with me, work it out, you can. Or if you want to just listen in and we'll do it together, that's fine as well. So the first one, my dependent variable here looks like SAT. It's that left-hand side variable. So it's being predicted by some equation on expense. So SAT is my average state SAT score. So looks like we'd have 51 if we include DC in this. And expense is per pupil expenditure in thousands of dollars. Okay. So what this equation is telling me is that if I didn't spend any money on my students, which obviously in our data set's not going to happen, everyone spends something. but the average SAT score would be about 1,060. But that negative 22 is kind of interesting, right? What it's saying is that for every unit increase in expense, okay, so for every additional $1,000 that I spend on students, my SAT score, average SAT score, is going to go down because of this negative side by 22 points, which doesn't seem right, does it? The idea being that the more I spend on kids, the worse they do on the SAT. But remember, we're assuming that this includes everything. But this shows you how a simple linear regression fails to capture other variables that also influence SAT score and how much we spend on students. So if you think about the types of states that tend to spend more money in general and more money on students, those tend to be poorer states. And we know that the relationship between poverty and student test scores is negative as well. So there are some things we're missing here that aren't capturing why this relationship is negative. You don't want to run to our congressman and say, stop spending money on kids or spend less and they'll do better, right? That's clearly not the implication. But we have to think about the other variables that aren't included here. So this just highlights some of the weaknesses of doing the simple linear regression. Excuse me. All right, number 2. Birth weight. So birth weight here, my DV, is predicted by number of cigarettes, okay, that they smoked during pregnancy. This is tragic. So the birth weight, if I don't smoke any cigarettes, if my mother didn't have any and she didn't, the average birth weight in this population, so the United States, let's say, would be 119 ounces. But for every additional cigarette that my mom smokes per day or during pregnancy, my birth weight is projected, that baby's birth weight is projected to go down by 0.5 ounces, 514 ounces. Okay, so that's how that birth weight is what's the change, right? So for every cigarette that's smoked, birth weight's predicted to go down by 0.514 ounces. Okay, and the final one here, we have salary, left-hand side variable, the DV, being predicted by return on equity of a CEO's firm. So this is saying for each additional unit increase in ROI, or ROE, excuse me. So for each unit change in ROE, for each increase, the salary of a CEO is predicted to be increased by 18.5. And now this is in the thousands, okay? So if they have zero return on equity, their average salary is going to be close to $1 million, right? But for each one, we get about an $18,000, almost $19,000 bump, okay? So that's how we're interpreting regression coefficients. So hopefully you're able to kind of follow that intuition. And there are other examples in your book that you can go through. Okay, so we haven't left hypothesis testing. That was just more explaining the kind of backbones of how everything works. So now we need to think about all this in terms of the concept of the process that we've been moving through. So given this simple regression equation model, what is the null hypothesis in terms of defining the relationship between X and Y? And what would the alternative hypothesis be? So we can state this in plain terms and we could say, well, there's going to be no relationship between X and Y, or there will be some relationship between X and Y as the null and the alternative respectively. But remember, that relationship is defined in this equation by beta 1. So a quicker way to say that would be that beta 1 equals 0 for the null, or that beta 1 is not equal to be 0 for the alternative. Okay, so we have our regression equation that's defined some relationship between X, the independent variable, and Y, the dependent variable. We have our null and alternative hypothesis, the null hypothesis stating that beta 1 is equal to 0, and beta 1's not equal to 0 is our alternative. So now we need to calculate a statistic. Well, in regression, we use the t-statistic. And we assess it, we calculate it, not like the formula you had previously, but now using the information that we have from our regression equation, we calculate the t-statistic by taking beta 1 over the standard error times beta 1. Okay, that's a quick way to calculate our test statistic, which is our second one. So on the next slide, I'll talk about, well, how do we find the standard error? All right, so with statistical significance, just as before, we need the standard error to understand whether or not, to standardize our beta and to understand where it lies within this distribution, to know to calculate its p-value. So the process for doing that are using these formula below and knowing the degrees of freedom. The degrees of freedom for this t-test will be the number of independent variables minus the number of observations minus the number of independent variables, which in this case we just have one independent variable. So that's the degrees of freedom, and then those are the formula. And I'm not going to walk through those. We're going to have Stata do those, and then they'll be in Quant 2, you'll follow up and dig in deeper into how these standard errors are calculated, but just know that they're associated with both the intercept and with the slope term, that you have some standard error associated with those. So as I mentioned, Stata is going to go ahead and report our coefficient estimates. That's both the intercept, the beta 0, and the slope parameter, beta 1, the standard errors associated with each one of those, and the t-statistics. And remember, we can calculate the t-statistic for our beta 1 by taking the estimate that we have from our sample of beta 1, that's why we have the hat there, it's just to show it's an estimate, over the standard error of beta 1. And when n is large, the critical value at the 5% level for a test of significance for two tails, as we know, is plus or minus 1.96. So often we just approximate it close to 2. So if our t-statistic is greater than 2, often we say, well, that's statistically significant at the 5% level. Okay, so just to bring it back now to conclude today's lecture, we talked about correlation coefficients and regression, simple linear regression. While a correlation coefficient quantifies a relationship between two variables, it does not fit a line through the data, okay? And so with correlation, we don't think about cause and effect. We don't think about your weight causes your height to be different, your height, your weight, or something like that. We're just showing how two variables are related to each other. But with linear regression, we do posit some direction. And we say, well, how does manipulating or varying x lead to changes in varying y, or the dependent variable? And that linear regression line is going to be the line of best fit that predicts our y from x value. So you give me an x value, like students SES, and I can give you a y value, like a test score, if I have that linear regression equation. Just as with the correlation, we talked about R-squared, it also fits within a regression context as well. And it's going to be the proportion of the variation in y that's explained by x. So what's the percentage or proportion of how y varies that we can explain, attribute to x, okay? And Stata is going to give us the R-squared value for each of our regressions. Okay, and regression can also replace t-tests. So even though we've been talking about in the context in the relationship between two quantitative variables, we can use regression for categorical variables as well. So imagine a case where we have a quantitative outcome, a quantitative dependent variable like height, and we want to know how men and women are different. So we can run a t-test on that. Well, I can also run the regression equation on that. So I can regress, we always do y on x, so I can regress difference in height, so height on gender or biological sex, male and female, okay? And so to do that, we just create what we call a dummy variable, where if it's on, you're a female, it's a 1. And if you're a male, it's a 0. And that coefficient, that estimate that I get, is going to predict the difference in height between men and women, okay? And the standard error will tell us whether or not that difference is statistically significant. And we can go ahead in class when we work together in Stata, we can show how both the t-test, independent samples t-test, and the regression equation will give us the same answer in both cases.